Hello. Um, Professor Mori did his PhD in Kyoto University under the supervision of a great mathematician and commutative algebraist and algebra geometry, Professor Nagata. He obtained his PhD, he graduated in 1978. Hironaka, another algebra geometer and field medalist, once wrote, "To classify algebraic varieties has always been a fundamental problem of algebra geometry, even an ultimate dream of algebra geometers." He wrote this one around the middle of the century, of the 20th century, and not much was known at that time for classification of algebraic varieties. The Italian school at the beginning of the 20th century made the first significant progress. They classify no singular projective surfaces. Their method cannot be generalized to higher dimension, and Zariski and Kodaira made some contribution along the 20th century. Mori was awarded a field medals at the 1990 ICM in the city of Kyoto, the same city that he got the PhD. He received the medal for his remarkable work in a period of 12 years between the 1978 when he graduated and the ICM in 1990. Among the work he did is the classification of Ano threefolds and the minimal model program, known also as the Mori program. Hironaka again, after the results of Professor Mori, he said the following: "The most profound and exciting development in algebra geometry during the last decade was the minimal model program, connection with the classification of algebraic varieties of dimension 3. Mori initiated the program with a new and powerful techniques, guide the general research direction with some good collaborations along the way, and finally finish up the program by himself, overcoming the last difficulty." That was Hironaka. He has received many other awards, among them in 1990, one of the AMS awards for the work he did, and several other awards. Now, I'm not the one giving the talk today, so I'm going to stop here. And it's a pleasure and an honor to introduce Professor Mori.
Thank you very much for this. Shall I start? Yeah, thank you very much for the nice introduction. Later I'll explain how I have been doing it, and it may disappoint you that it's slightly different from the introduction, but anyway. So first, I'm very much honored to be here at the 75th anniversary of this Math Institute. It's not easy to achieve 75 years of history. So I'm currently officially a member of Curious, which is only 2 years old. And the other one, much older. So 4 years ago, we had a 50th anniversary. And I happen to be the director, so I know how difficult it is. So, and I couldn't do anything without the support of the older members. So it must be the same with you, Jose. So I have to congratulate you all, and it was a great experience. Okay, so let me start. So I think it's the best way to show you how things were around the time 1975, which is, well, this is just a coincidence, 75. This is the time I started my research in algebraic geometry as a research associate. Yeah. And okay, so this page is really not for you, but this is just to illustrate what are the algebraic varieties. And so it's a solution set. So first we consider all the coordinates. The coordinates are complex numbers or real or positive characteristic, depending on the situation. So basically, we look at a polynomial equation. And for this arithmetic operation, it doesn't matter whether the field is a real or complex or even positive characteristic. But when we draw a picture, there's some slight difference, but it's okay. Yeah, okay, so let's forget about it. Yeah, so classification of algebraic variety. So this is the main theme. So we want to classify, well, in this case, I just wrote one equation, but it could be a set of equations. And so this is the easiest example. So graph is birational to, or even isomorphic to the x-axis. And this is possibly the first non-trivial example. I learned this in my high school days for the entrance exam. Well, this is a circle centered at the origin. And from -1, 0, you draw a line with slope t. And then this line intersects another point, except for this -1, 1. And it is, the coordinate is given by this formula. You can easily do that. And so this is a birational or a coordinate change or birational transformation, whichever. So from t axis to the circle. Yeah. And so this is a typical example of a rational curve. So this means that it's a curve with a rational parameterization in one variable, like this. And so here I draw real solutions, but as I said earlier, we don't really care whether we consider complex or real. Just depending on the situation, we choose the convenient one. So let's start with the dimension 1. So algebraic curve, it's except for finite number of points, it is embedded into one of these, the Riemann surfaces of genus G. So when G is 0, it's a Riemann surface, and G equals 1 torus. And for bigger G, it's this shaped donut. And assuming that we work over complex numbers, and assuming that we put some metric. So in principle, I mean, essentially we don't consider a metric, but just for illustration, let's put metric and see how a curve is curved point. And in this Riemann surface case, it's positively curved everywhere like this. And for G equals 1, it's flat. And for G bigger than 1, it's like saddle shape. So for dimension 1, these are the 3 typical geometry. And the idea is we want to generalize this in some way in higher dimension. But anyway, this is done in the middle of 19th century. Then algebraic surfaces. So in case of algebraic surface, there is a totally new phenomenon. Given a surface and a point P on it, we can blow up the surface in the sense that we remove a point P. By the way, I'm only considering smooth surfaces. I don't want to consider singularities at this point. So remove a smooth point, then it's a surface. So its tangent space is C2, two-dimensional vector space, two-dimensional space. So its tangential direction gives you P1. So we put back P1 in some way, which is called -1 curve. So given any point P on the surface, we can sort of blow up replace P and put back P1 in a systematic way and produce another smooth surface S prime. That's what's called blowing up. Okay, replace P with P1, keeping the rest the same. And C is a rational curve in the sense of the previous slide. And it's called -1 curve. The reason is that if you consider the self-intersection, it's a -1. Anyway, it's not a serious matter. And this map from upstairs, we call it contraction. From downstairs, it's blow up. That way. And the idea of birational classification of algebraic surfaces is to classify them up to this blowing up contraction. And this is very much based on the minimal model programming dimension 2. So this is around 1900. But in those days, minimal model had a slightly different meaning. I'll explain that later. Okay, so I'm going to explain the minimal model programming dimension 2. So if X, the surface X has a -1 curve, we contract it. And since X prime is smaller, apparently, it's easier to work on X prime. So we work on X prime. And we look at X prime and see if there is any -1 curve. If there is, we contract and keep doing. And until there is no -1 curve. Well, you may wonder what if it continues forever. But each time you contract, the second Betti number drops by 1. So it stops. Then when it stops, it's either P1 bundle or P2. This is the picture of P1 bundle in my mind, and P2. So these are the cases involving G equals 0, genus 0 case. And this is a geometry you have in mind. And the other case is a minimal model. So this corresponds to G equals 1 and larger. So we don't distinguish these two cases sharply at the moment. And so in those days, the theory was very difficult. So for instance, to find -1 curve, there was a method called adjunction terminates. So case-by-case analysis finds you a -1 curve to contract. So it's a combination of arguments, and it's quite difficult. And so at the moment, I just present you difficulties only. Okay, so in those days, still people want to generalize this to higher dimensions. Okay. So there are examples for smooth threefold with smooth surface, which looks like being contracted to a smooth curve. This is exactly the three-dimensional analog of the blow-up. And in analytic space, under certain numerical conditions, you can legitimately contract X to analytic space X prime. Okay. And so we may expect that if X is projective, so is X prime, and we can keep contracting. So there are examples where X is projective, but X prime is not projective. But you may think that, well, we don't care about projectivity. We go on. Yeah? Then if there are examples where X is not projective, and if you contract it, X prime is no longer even algebraic. But at this point, I stop. So it's quite involved to go in this direction, meaning looking for smaller varieties. Yeah. And there are some other activities around 60s and 70s. So this is an example by Hironaka of algebraic and birational morphism of smooth threefold to smooth threefolds, which is not a composition of this kind of standard blow-ups. Since it's fun, I'll show you in the next slide. And since in those days, minimal model program seemed impossible, and of course, at least not a very practical project. So people try to classify the algebraic varieties without minimal models. So that's Itaka's school. And there are people who constructed the example where smooth threefold doesn't have a smooth minimal model in any sense. That's by Ueno. So those are the examples known at in those days. So this is the time I started working on it, and I was very curious about this, but I didn't know how to do it. And also, as introduced, I came from commutative algebra. So these are the birational classification mainly worked by people in Tokyo University. Tokyo and Kyoto, though names sound similar, it's quite different. In Kyoto, people are mostly working on commutative algebra. I was one of them. Yeah. Okay, anyway, that's how things are. Okay, so this is example. So start with a smooth threefold. Just take three curves, smooth curves, meeting at a point transversely. So this could be connected into one irreducible curve, but let's not think about it, and just three totally different curves meeting transversely at a point. Okay, then somehow Hironaka came up with a very strange blob. In his paper, he just listed ideal. So in terms of, so start with coordinate x1, x2, x3. He exhibits ideal, some complicated ideal, and says that if you blow up, you get this way. Okay, so this one in the middle, you get P2, and there are P rational curves. Somehow I drew with red, but this is something I will do that later. Yeah. So somehow this is not a composition of a smooth blow-up. One reason, one way to look at it is that if you know how a smooth blow-up looks like, it's either a P1 bundle or a P2. Exceptional divisor is either P2 or a P1 bundle. In this picture, this is the only possible thing. And so, of course, we try it, we contract it, then we get a singularity. So it cannot be a composition of a standard blow-up. Okay, so I'm going to explain how my heuristic grew. Okay, so possibly it's easier to show you the topics I have been interested in. The first topic is something called the Frankel conjecture or Hartshorne conjecture. It's about a very special variety. Apparently nothing to do with birational classification in the general picture. Then somehow I could prove it. And then once I proved it, I found something called extremal array, which I'll explain later. Then there are two directions, birational classification and biregular classification and minimal model program. So this is the main topic I'm going to talk about. But you see, this is a very general problem, but somehow it started with my curiosity on a very, very special problem. Okay, so we come back to the question, how a variety is carved. Okay, so again, although we don't have to consider the metric, but to illustrate or to study how a variety is carved at a point, I introduce a metric. Okay. And then for each plane in tangent space of a point, I can consider the geodesic along that along a vector in this R2, and I change all directions, and the geodesics will sort of sweep out some picture like this. So in this case, it's all geodesics sort of in the same direction. So this is positive. And in this case, it goes up and go down. And this is negatively curved. And or somewhere in between. It's hard to tell. So yeah, so Frankel conjecture is about this first case. Okay, so it asks, what if a variety X is positively curved everywhere for all P and all directions? And the conjecture says that there is only one such in each dimension, the projective space. Okay, so this is the precise statement. So it is about a Kleiman manifold. And Hartshorne sort of modeled upon this differential geometric conjecture and came up with the algebraic geometric one. So he simply replaced this positive curvature condition by ampleness of the tangent bundle. So this is where I came in. So okay. So first I considered a dimension 3, which was where the Frankel conjecture was solved by Mabuchi, and I looked at the preprint, and I became very curious as an algebraist. So I could see some way of applying derivation for studying this conjecture. So with my advisor Sumihiro and I could manage to reduce this to this Frankel conjecture. I forgot to say that this condition, differential geometric condition, is stronger than this algebraic geometric condition. So we could prove this by some extra observation on the derivation. Okay, that's how it goes. But the method didn't work in higher dimension. It worked only for dimension 3. So I had no idea how to do it in higher dimension. Okay. So that's around 75, 6 or so. Yeah, so and 79, I could somehow prove it, but I'll explain that later. Okay, so this time I want to consider algebraic geometric measure. So earlier I talked about the differential geometric measure to check how a variety is curved. But those are not algebraic measure, algebraic invariants. So if we consider a curve C and consider all those curvature in the previous page, for all P and all planes in the tangent space, we get this intersection number up to some absolute constant. So this is the invariant I want to look at. And so for sake of saving time, this is the condition. This is the condition I'm going to use for the minimality of the variety. So apparently, it has nothing to do with the minimality of the variety in the previous slides. But later you see that how it is related. And so various positively curvedness. So the top one is the one used for the Frankel conjecture, so much stronger. And the positive ampleness of tangent boundary is weaker. And if a tangent boundary is ample, so it's determinant. So anti-canonical bundle being ample is a weaker condition. And then this positively curvedness along C is a further weaker condition. Okay, so this is the condition I will use later. So I will explain a little bit about how I could solve Hartshorne conjecture. So I said I could solve dimension 3 with the advisor, but the method didn't generalize to higher dimension. And I didn't know how to do it. But when I was trying to prove an intermediate statement, I thought I could prove it, but there was a mistake. And when I analyzed it, in the process, I found that I somehow produced a rational curve. So this kind of statement. And once I found the rational curve, the rest is very, well, it came out very easily within a week. Yeah, so it's quite, it's a totally different approach. So once you have a rational curve, you can make use of it and get a statement on the variety. That's the basic attitude of my rational curves on algebraic varieties. And for some people, this was very annoying because even for such a naive characteristic zero statement, I had to go to characteristic P, positive characteristic. So when Stu and Yao proved Frankel conjecture, Frankel conjecture, they must have tried to produce this kind of thing, but it's quite difficult, and it's still not known how to prove this without going to characteristic P. Yeah. So if you can prove this only in characteristic 0 without going to characteristic P, you may be able to do something about symplectic manifold and so on. So I was told that in complex dimension 2, one can find a rational curve in symplectic category, but they use all kinds of advanced techniques, sort of minimum model program. So it's not the kind of answer I want. Okay, so yeah, so this is the statement I mentioned. And I explained just a little bit how to find a rational curve. Okay, so since Nagata's name was mentioned, I put it here. So the method is really using the notion of schemes. So this is my favorite picture. This is the illustration you can find in the book of Mumford. So bottom is spec Z, and for each prime, you can find some geometry of characteristic P. And this is the picture of a scheme of P1 over Z. And so the basic idea is that if we are given an algebraic variety in characteristic 0, you can extend it to characteristic P. Most characteristic, except for finite number of primes. So you can work on characteristic P. And in characteristic P, you can use Frobenius, and you can somehow produce a rational curve. And once you have a rational curve, you somehow bound the degree, and you find a rational curve on almost all primes. And if you can find a rational curve of a bounded degree for almost all prime, it has to come from characteristic 0. That's a simple statement. I mean, I don't prove it, but it's quite simple. So this is something like yeah. So in analysis, you don't have anything of this kind. Like we don't have any semi-algebraic set in algebraic geometry. So it's a fair deal. So outcome of rational curve. Yeah, so using this rational curve, I could prove a Hartshorne conjecture, but I wanted to do something more. And so in search of the application of algebraic curves, I found the notion of extremal rays, and which gives a way to study a more general problem. So find the key structure of a variety X, which is positively curved along some curve C. Or how to find the key structure of a curve along which a variety is curved positively. So the general philosophy is that usually, I mean, we expect that a variety is negatively curved. If it is positively curved along C, there must be some geometric reason. So that's what I'm going to explain. So I start with Kleiman's cone of curves. So X is an algebraic variety, and given so complex algebraic variety, given a curve C, we can define the algebra. It's homology class of C, which is H lower to H lower to XR. So it's a finite dimensional vector space. So it's for each curve C, we have a vector. And we consider all the curve C, and we consider the cone spanned by those vectors. That's C of X. So C of X is a genuine invariant. Okay. And it looks like this. So at the moment, this doesn't mean anything, but in the next slide, I'll explain. And Kleiman introduced this notion to study projectivity. And we only use one way. When X is projective and take an ample divisor, say L, then if we consider the vectors which have intersection number 1 with L, you get some bounded shape. It doesn't go through the origin. Okay, so instead of looking at the whole cone, we can only cut the slice, cut the cone by slice, say L equals 1. So at this point, I just, how to say, I'd like to show you how I feel. Algebraic variety is something we don't see, we cannot see in dimension 4. Even complex dimension 2 is real dimension 4, we cannot see. But somehow algebraic geometers, or maybe just not algebraic geometers somehow draw invariant on their the canvas in their mind. Yeah. So this is what I'm doing when I do research. Yeah. Okay, so geometers study figures via invariants. I used to say algebraic geometers, but I try to be on the safe side. Yeah, so invariants are similar to abstract painting, but there's a sharp difference. Unlike art, it needs objectivity and reproductivity. So in art, it cannot be produced in mass production. Yeah. And also, anyway. So an invariant is defined for each figure. And so here is the difference between differential geometry and algebraic geometry. So in differential geometry, they have, are there differential geometers here? In differential geometry, they have fine-tuned tools to study a shape, like this curvature and all those things. But in algebraic geometry, we don't, as I have shown. So the pictures we draw in my mind is not really concrete painting. It's rather abstract painting. And this is like a cubism. Yeah, I think this is a good break for you. Yeah. And this is a picture I like. So it uses only circles and lines. And somehow it is a picture of a lenient grandpa. You can somehow see, but, you know. And Pavkura says that art does not reproduce what one can see, but makes seeable what one cannot see. Somehow this applies to algebraic geometry. Yeah. So I come back to extremal array. So what I could find using the rational curve and the extremal array is that we look at this cone, and then on this cone, on this space, Kx, a canonical divisor, works as a linear function by intersection number. And k equals 0 gives a hyperplane. Of course, it can be empty, can be 0, or no, it can be the whole thing. But, positive is half space, and negative is also another half space. And I'm saying that on the negative side, negative half space, the cone is sort of polyhedral. It looks like this. There may be infinite number of them, so it's not really polyhedral in the genuine sense, but still, it gives you the kind of feeling. So the ridge line like this, giving this, are called the extremal array. So X is a minimal model if Kx is non-negative on Cx, or equivalently if there is no extremal arrays. Okay, so So as an algebraic abstract painter, so this is my picture, and I draw these ones, and I want to see what the meaning of this. That's a very natural question. Yeah. Okay, geometric meaning of extremal rays. So I come back to the surface case. So in the description slide of the extremal minimum model program for surfaces, there are a few cases. So P2 and in my earlier explanation of minimum model program, I considered -1 curve, contracting -1 curve. And if there is no more -1 curve, either I get the P2 or P1 bundle, or oops, I forgot. Sorry, yeah. I assume that there is an extremal ray. So there are 3 cases. And somehow we are reproducing the same picture in the minimum model program in the earlier case. And the difference, so there is a difference. The difference is that this time we know where to look and where to look the -1 curve and the structures. And it gives a much simpler proof. And it works when there is a group action. If there is a group action, extremal ray is defined as the edge of a very natural object. The group acts. If there is a group action on the X, it acts on the cone. Yeah. So one can use extremal rays to do higher dimensions. But to do that, we immediately have problems. So it's a singularity. So we contract something, we may have a singularity. And so around the time I introduced extremal ray, Reid also found this new class of singularities. So imitating a case of surface, I can consider threefold and apply minimum model program, meaning if there is an extremal ray, I do something. And in Hironaka's example, I showed you that there is a P2 whose contraction gives you a singularity. That's exactly this case. If you start a minimum model program, sorry, I haven't really explained what minimum model program is, but in a few moments I will. And then I will get a singularity, and to continue the program, I also have to find a framework which contains variety with singularity.